There'll be some time lag. Hi everyone, thanks for coming. Yeah, so this will be the first session, AI Lightning session. Thanks so much to Jeremy and Rachel for being encourager and accepting a request to kick off the session. Before we jump into the sessions, some logistics. Here's the timer. Hopefully it will be visible to the speakers. So we'll have a countdown clock there. All the talks will be capped at 5 minutes and 2 minutes for question and answers. And don't worry if we don't get to all the questions. We will have forums for each individual speaker so that we can all continue the discussions. Without further ado, I would like to welcome Rachel to share her story around fast AI, among others. Rachel, do you want to come before this screen?
Okay. Yeah. Okay, now I can see this. Okay. So I'm Rachel, and I'm going to talk about my story of co-founding Fast.ai. I'm going to start back in high school because I've never liked exclusiveness. I went to a very poor public high school in Texas. It was very racially diverse. It was 30% white, 30% Latino, 40% Black. And a lot of the wealthier, whiter school districts around us had a very exclusive and sometimes racist attitude. And I also saw that they had access to a lot more resources than we did. And I really hated that inequality and disparity in kind of educational access. Skipping ahead to 2013, since this is a lightning talk, I was working as a data scientist, and deep learning was starting to win a lot of Kaggle competitions, so I was very interested in it. This was before any of the open source deep learning frameworks had been released. I watched Geoffrey Hinton's videos on Coursera, and then I went to hear a pretty famous researcher was speaking at a meetup. I was very excited, and his talk was pretty much purely theoretical. And during the Q&A, I asked a question about how he had initialized his weights. And he said, oh, that's part of a dirty bag of tricks that nobody publishes. And at the time, I was really disappointed, just feeling like the field was so exclusive and kind of inaccessible because everyone doing it had studied with the same 4 PhD thesis advisors, and then they weren't sharing the practical info. Also at this time, I was working for a tech company that was very popular, but I was very, very unhappy there. And people were kind of constantly saying to me like, oh, you're so lucky to work there. You're lucky to have this job. And I wasn't happy and kind of felt like, do I need to settle? Like maybe this is as good as it gets. And I gave up on going to meetups and deep learning for a while. Skipping ahead now to 2015, I had my daughter, and it took me about 8 weeks to recover from giving birth. So I was mostly lying down during that time. And Andrej Karpathy had released his CNN course at Stanford online for free. And so I read his slides, I read them aloud to my newborn. And when I was feeling better, I coded all the assignments, and I thought it was fantastic. That was the most accessible introduction to CNNs I had seen. And at this point, Caffe and Theano and Keras had been released. I think this was kind of right before TensorFlow was released. And so these are really positive steps, Andrej's course and having these open source frameworks available. But Jeremy and I still felt like a lot was missing. Most of the research was happening at Google and OpenAI, and they just have so much money and so much data and so many GPUs that I think they're not even aware of kind of the situation that most of the world trying to do this is in, with very limited resources and often with much more practical problems, whereas their research focus tends to be more theoretical. With starting Fast.ai, so our goal was we want eventually for anyone, anywhere with limited resources to be able to use deep learning on the problems they care about. And that felt like such a kind of grandiose and maybe somewhat vague goal that I found it embarrassing to tell people what we were doing at first, because it's so ambitious. And we did it now, we were gonna do it, and we still don't know how we're gonna do it. we tried a few things that didn't pan out, but we realized pretty early that a cycle of iterating between research and teaching would be helpful for us. And just as we've told you with deep learning, to always start with kind of the simplest model possible on a small sample data set. That's what you all are for us. We were like, let's start by seeing if we can teach coders who will put in 70 hours of time to use deep learning. And when we proposed this class to USF, we weren't sure if that was even possible or how we would do it, but we knew we would try our best. And I think it was also important for us to kind of make this commitment and put ourselves on the hook of, okay, now we have to deliver. Yeah, and so that's how we've started. I've been very excited about how things have gone. I hope you are too. If not, let me know. And we're, yeah, less than a year into Fast.ai's journey, and I'm excited about where we'll go in the future. Thanks.
Can you share some of the things which did work?
And some of this is also time. So like, I mean, we'll come back to these. So there's a language called J, which is a descendant of APL for really vectorizing math operations. And it has a really neat notation. And so we felt like there's like some potential there to be able to kind of program more concisely. And yeah, and it's a total mind trip to learn, because you like something that would be like 20 lines of code in another program is like 9 symbols, but like the way those symbols are put together. So that was something, but I think we're going to return to that we kind of were like studying some last year that we set aside. And then I think we're going to go back to this too. We're kind of working on some super resolution, which like we have returned to with the course, but that we kind of put aside. Any other questions? Yes? Well, so my personal focus in May and June will be on teaching a numerical linear algebra class at USF, which is getting computers to do matrix operations very quickly and with acceptable accuracy. I'm actually not even sure what, we want to come back to, like, I mean, one of our goals is to make it easier for people to deploy apps. And so we're hoping to make kind of several test apps and deploy them to see kind of what the pain points in that process are. So I think that's something we'll probably return to this summer.
And one last question. How do you measure your progress, right? So how do you know if you can improve on what you're doing?
That's a good question. Yeah, I guess it's somewhat subjective, and I mean, I find a lot of satisfaction of when I'm able to help people and kind of like getting positive feedback around that. Something Jeremy and I were talking about earlier is that I think I've also had to recognize things that I'm going to do less of to have more time for the high priority stuff. And so like I'm right now putting a lot of time into preparing for the course I'm going to teach in May. That's really important to me, but I had to kind of choose like, okay, I need to like go to less conferences and go to fewer meetups and kind of decide like these are the things I'm going to put less time into. Thank you.
And now we'll have Jeremy come and talk to us. Thank you, Jeremy.
Hi, everybody. You've seen enough of me already, so I'll be quick. So I thought I'd tell you a quick story about a impact project that I did just before I did Fast.ai, which is called Enlitic. I guess the story for me also goes back to high school. I don't know, for some reason at high school I got the idea that one day I'd like to build my own thing. I don't think I knew it was called being an entrepreneur at that time, but I just had the idea of like building something myself. It took longer to do that than I probably should have, but eventually I did start 2 companies that were successful and built them for 10 years and sold them. And they reached a point in my mid-30s where I'd achieved everything in my professional life that I'd set out to do when I was 16. And there was this sudden realization when my mum told me, you know, you must be so proud because, you know, I know that's what you wanted to do, and I wasn't at all proud, which was a bit of a shock to realize I'd spent over half my life working on doing something which wasn't going to make me proud even if I did it. So I guess the problem really I realized was that the companies I'd built were focused on being a successful company rather than on successfully making an impact. So I kind of tried, after I sold the second of them, I tried basically doing volunteering and as a way to try and make an impact. And that was a really frustrating experience. I found that as a volunteer, people assumed that I had very little to offer, and that my level of commitment would be very low, and my level of competence would be very low. So that was a total failure. So I don't know, one thing led to another in terms of, I don't know, I accidentally found myself at Kaggle, and like Rachel through Kaggle realized deep learning was going to be, you know, bigger than the internet. And that really took me back to my early days after high school when I was very confident the internet was going to be huge. And unfortunately, I listened to other people who all disagreed with that rather than listening to what I believed in, and I didn't do anything about my feelings about the internet. So I thought when deep learning came along, I thought, okay, I'm lucky enough to have a second chance. You know, there's a second revolution coming, and this time I'm not going to miss it. So I left Kaggle and decided to focus on like, okay, what's the biggest impact thing I can do with deep learning? This is not the way I would recommend anybody normally starts a company. Having a tool and looking for a nail is a really bad approach normally. But I was lucky enough that I, you know, made enough money that I could spend a year researching it. So normally I tell people to scratch an itch. You know, if you want to build something that you're very familiar with the area. But in this case, I felt like I had enough time to just really find the highest impact thing. Through that year of research, it took about 6 months to realize the highest impact thing would be medicine. Another 6 months to kind of figure out roughly what part of medicine might be a good place to start and what might be the opportunities there. But when I started Enlitic, I didn't really know what I was doing, but I knew that it'd be easier to get there if lots of people assumed that I did know what I was doing. So I kind of did a splashy launch and, got some press around it. And, I didn't make any promises that weren't true, but I just kind of, tried to get some enthusiasm around it. That helped me get some good people involved. It was still just 4 of us. And it kind of made us feel like we were on a bit of a mission, and that we had to deliver on this vision. So we focused on trying to create one good demo, one good prototype. So we decided to do lung cancer diagnosis, mainly because the data set was readily available, and we thought it was a really good story and high impact. And it worked. I was pretty sure it would work, based on what I knew about deep learning. I would have been surprised if it didn't. And so on the back of that, we were basically able to get lots more publicity, which led to more funding, which kind of led to a nice cycle of, positive feedback cycle. Yeah, so Enlitic was able to kind of accelerate from there.
So one of the online questions here is like, do you plan to make Fast.ai course ongoing with courses as the new cutting edge methods come up?
I'm not sure we have any specific plans, but like Rachel said, our general plan is like do research, teach, do research, teach. Each time we have to teach something, it means that it's not easy enough that you can't do it without teaching it. So we'll try and make it a little bit easier to teach. That requires some research, and so that's as far as our plans go at this stage. Is basically to kind of go back and forth between teaching and research, continually trying to make it so that there's less and less to teach, and also trying to make it so that the bar to start learning is lower and lower each time. That's got nothing to do with my talk, though.
And one of the questions, other questions were what do you suggest to young entrepreneurs? Like, what are the pitfalls to keep in mind before you jump into leave a particular job which you are doing and then jump into something?
I guess the pitfall is doing what I did, which is picking a tool and looking for something to apply it to. It's much better to start with a problem which you're deeply familiar with. So if you've worked, as a chemist doing a PhD and you're deeply familiar with the kinds of problems that chemists have to deal with during their research, then build something for them, or if you've spent time, working part-time as a recruiter, then you know exactly what recruiters have to deal with, build something for them. Build something where you know that there are people in the world who care about the thing that you're building and whose life will be, non-trivially better if you're successful at building the thing. I think the biggest problem by far I hear is people saying that they built something and it turned out nobody needed it or wanted it. Oh yeah, that was not with deep learning. Yeah, no, that was not with deep learning. So it was very, very surprising to me. So I was like the #1 on Kaggle in 2011, I guess, 2011. But I had no technical background. I had always been interested in data, and like all of my work, I tried to always use a data-driven approach. But when I was in management consulting, I was a business strategy consultant, telling people how to react to a new competitor in the marketplace or whether to go ahead with the merger or whatever. Like it wasn't data analytics per se, but I always tried to use a data-driven approach. And I think because I was 10 years younger, at least, than everybody else, and they were all able to use their authority and expertise, and I couldn't. I had to use data, so I kind of was forced to. Anyway, so I was very surprised when basically after I sold Fastmail, I entered a Kaggle competition because I wanted to learn R better. Like I'd used it a little bit, but I didn't know it well. And yeah, I kind of thought I'll enter under my own name because like most people use monikers, I guess. I'm going to enter under my own name. I will take responsibility for it, so I just try not to come last. Yeah. So somehow I won that competition, and I was just like, I was really shocked because I thought like all these other people in the competition pretty much all had PhDs or were professors or whatever, and I kind of had this sudden realization of like, oh my God, this high-end technical education stuff is at least sometimes less important than having some common sense and basic data management skills. So yeah, so I was doing a lot of stuff with random forests, basically, and Excel, and I wrote everything from scratch pretty much actually in C# when I was programming. So they're all my own libraries, which I think helped a lot. I had used neural nets over 20 years ago in marketing, retail banking, marketing, and credit scoring, but then I kind of ignored them for 20 years because, yeah, they weren't really the state of the art for anything. So when they reappeared a bit in 2012, I wasn't surprised. I always thought, like, okay, this is the right way to do things, and I was kind of surprised that they did disappear. So when they came back, I was very much ready to, very open to the idea that they could be very successful.
Thanks so much, Jeremy.
Okay.
Next, Summer, are you ready to go?
Yeah, sure. Can you hear me?
Yeah, we hear you. Awesome.
Okay.
So we have Summer talking about Urdu word embeddings. Very exciting. Thank you so much.
Yeah. So can you guys see my screen?
Not yet.
Yeah.
Oh, we can see his screen now.
I can see that.
Yeah, now we can see it.
Okay. Right, so my name is Samar. I am from Lahore, Pakistan, and I work as a research assistant in a lab that focuses on language. So my talk today is about using stuff we learned, particularly in lesson 5, word embeddings for embedding NLP for languages that really have no resources to help otherwise. So the problem is really, if you get into research in any of these languages, there's really no data to train anything on. So it's like a life without something like from an educated corpus and word instead. And if you go to labeling data yourself, then Mechanical Turk doesn't have the expertise generally for these languages. I searched for Urdu and I couldn't really find any tasks. And doing all of this in-house requires hiring linguists, and it's slow, expensive, and really not something you do on a budget. So then just hypothetically, you are getting data and then having research and just really you end up doing that. So one of the ways to break out of this is to use unsupervised learning. To, in a way, help us get somewhere, which is better than having nothing at all. And something I've been exploring in my free time was using unsupervised learning and unreliable data in an attempt to just maybe get some improvement in the students and Urdu. So Urdu, for those of you who know, is the national language of Pakistan, and it's actually the 11th most spoken language in the world. You might have, if you watched Bollywood movies, then Urdu is probably what you hear, and it's very close to Hindi. So, am I still transmitting? Hello?
I can hear you.
Can you hear me? Or did you guys mute yourselves?
No, I can hear you.
Okay, great.
Yeah, we can hear you.
Right, so I obtained multiple corpora of Urdu from the internet, and then I also used the Wikipedia Urdu dump. And this totaled about 150 million tokens. And then I trained what Google offers, the simple word-to-vec model with the standard settings, continuous bag of words model, to learn 100-dimensional word embeddings. And this kind of marked the first time such embeddings had been trained at this scale for Urdu. I ended up with a vocabulary of 175,000 words, which might seem a lot. That's because Urdu is very, very morphologically rich. So a word in Urdu can have up to 70 surface forms. I would list them out, but I'm going to stick to the presentation. So the embeddings actually capture really incredibly useful semantic relationships. I'm sure in the class, for those of you recall, we sort of had an idea that when you learn these word embeddings, they bring similar words together in this vector space, and it lets you have interesting relationships between them. And this was, so before I get to the example, this was very interesting. For Urdu, for a language that has not been researched that much and has not been researched in this way, where you're just using machine learning alone to build a resource that can be so rich in meaning. When I showed this to my advisor, who's actually one of the top NLP guys in the country, he was really surprised because there's this disconnect between the deep learning community and what everyone else is doing. And I guess what this course was trying to do and was to bridge that gap. So once you bridge this gap between different communities, you can really do lots of interesting work. So we had lots of interesting examples here. I looked at the closest words to each other and then odd ones out and doing some linear algebra. The best example I could find was this. So on the right, you'll see the top word is the word I entered, and the next are the 10 closest vectors in order. And you'll see the translations on the left. So this captures, I think, at a very high level, the meaning of language. Yeah.
Sorry for the interruption. We don't see the slides rotating.
Which slide are you on?
We still see the first slide.
Really? Okay, hold on.
Maybe you're not sharing your presentation window.
No, I have. Hold on. Can you see? Screen share. Can you see?
We see the my work slide now.
Right. So you guys are just using this for all
Yeah.
this time? Oh, okay,
Yeah.
sorry. So anyway, so this is again. I'm gonna just move through them very quickly. This is the problem. You imagine a life without NLT Kit or Corpus and Mechanical Turk and really all of the data you find online. And one of the ways I found of breaking out of the cycle was to use unsupervised learning and unlabeled data to probably just get ahead a little bit in NLP for Urdu. And again, I told you Urdu is the national language of Pakistan. It's one of the most popular languages in the world. And I obtained around 115 million tokens from multiple Urdu corpora and the Wikipedia Urdu data dump and trained a CBOW model to learn 100-dimensional word embeddings. So this, again, marked the first time, and I have learned large vocabulary, did the morphology, really useful relationships. So these are the examples I really wanted to show you of the meaning these word embeddings had captured. So I hope you can see the slides now. Right. Okay. So I hope that's a yes. So on the right, you'll see the Urdu words, and on the left, their translations. The top word is the input, and the next 10 are in order the closest vectors. And if you really take a minute to appreciate the level of complexity and meaning this simple model has learned from unlabeled data, this is really amazing. And I showed it to my advisor, and he was really impressed by it, of what this simple model can do. So we've seen a couple of applications back in lesson 5. We looked at sentiment analysis from IMDb, and then we also talked about machine translation and all of this. I guess the best part about these word embeddings for a low resource language are that they drastically reduce the need for labeled data. An idea I've had is to probably use the word embeddings as inputs to a machine translation RNN, so it doesn't really have to learn these embeddings from scratch. I'm not sure how that'll work, but that's why I'm using this group as a sounding board to get more ideas. One of the probably most important things right now for a language like Urdu is to form the very simplest resources. WordNet is a very old resource, about 2 decades old, that has a list of words and synonyms for English. So even something like that for Urdu is, yeah.
Sorry again. We're out of time. We'll probably
Yeah, I'm
have to
done.
wrap up.
That's it.
Yeah. Oh, cool.
So yeah, so I'll probably leave you with thank you. And since we're talking about language, shukriya is the word we use here in Urdu. That's shukriya, and yeah, that's about it. Thank you.
Thank you so much, Samar.
Yeah.
Yeah. Any questions for Samar? Yeah. Yeah. We just want to make sure you're going to share the slides.
Oh, okay. Okay, sure.
Cool.
I can hear the question.
What direction do you plan to go next?
So next is in order of difficulty, I guess the first part will be building a WordNet. That's like words and synonyms. I tried a bit of that, but again, with meaning, you have synonyms and antonyms mixed together. So probably have to find a way to get the bidirectional relationships between different words. Moving on from that, probably some shots at, I guess, classification. Then translation. Translation is the one thing that requires parallel corpus, and we don't really have much of those for Urdu.
Cool. Thank you.
Yeah.
Next, Janardhan is coming to. Yeah, let's welcome Janardhan. That's mute. Okay, I'll mute mine. You probably need to connect as well, right? Okay.
Can you guys hear me now?
I guess it will be best if you connect so that not the walls and-
Can you guys hear me? Folks on online, can you guys hear me? Okay, yeah. So I would like to talk about a tool which I'm excited about. Like it's called the early detection tool for autism. So how many of you guys know about autism here? I think almost everyone. So good. So one of the things which struck to my mind after going through the course in Fast AI is like I have my niece who is like 5 years old and then like struggling with autism, and then my sister had a lot of pain in order to identify early in like whether the kid is like autistic or not. So that's the inspiration where I was trying to tackle the problem of if we are able to early detect using deep learning technologies the autistic kid, so it will be really good for all the entire population actually. And some of the characteristics of autistic kids is like they have restricted repetitive patterns of behavior and the interest, and there's no social or the interaction communication is lacking in these kids.
Would you mind doing the presentation also?
Sure.
It's probably on the slideshow.
Yeah. So basically, why do we need to study autism? So the pitch is about 1% of the world population is struggling with autism kids, and also there is a lot of cost associated with the lifelong care cost for an autistic kid. So it somewhere ranges between like $236 billion to 262 billion. So according to the Autism Society, so if we are able to early detect the autism, so we will be able to reduce 2/3 of the lifelong care cost for these kids. So that's the motivation to apply some of the deep learning technologies. And this is a normal child's photograph. And like this is a photograph from an autistic kid. So what I thought is like there might be some facial features which are very key in identifying some of the features which with the help of neural networks in order to say that this particular kid aged between 1 and 2 is having some features of an autistic kid. And also another pitch is like I haven't worked with the audio and the video. So they have these blabbering sounds these kids produce. So that might be a very good clue at the age of like 1.5 to 1.9. So wherein like we can catch hold on these blabbering skills and then like say this particular kid is like 60% autistic or 70% autistic and needs behavioral therapy. And in what happens in the developing countries is like a lot of people doesn't know what is autism. So even though the kid is repetitively behaving like this, so the mother or the father usually they do like, okay, my kid is like this, it likes these behavior. So that's what the conclusion is drawn from these kids. So in some way, if we can give an app to all the parents of the world, so so I have a mock-up of the app as well, like wherein like they upload the picture of the kid and then like they upload a 30 seconds audio document or like a video document. And then if we are able to come up with some of the results like, okay, this particular kid seems to have behaviors of autism, like 60% symptoms of autism. So we might be giving a small clue to the parent that they need to go to a very good doctor and then get it checked. It's not like the the foolproof tool, but like it's kind of like a detection tool for these kids or the parents, so that they'll be able to early detect this particular disease.
Thanks for sharing.
So any questions?
Actually, I thought it was interesting. So how do you photos that you train?
Yeah, so one of the challenging tasks is to get the photographs of these kids who are aged between that. But right now, I'm particularly working like with the, whatever the photographs or like the images what I have, and like also it becomes sensitive in like I have gone on to ask some of the people who drive these autistic behavioral therapies in especially in India. So there are a lot of people, they don't want to give this photographs of the images. So that's another challenge which I'm struggling with. But like I hope somebody will share. Yeah.
That's been awesome, actually. Interesting project and all that. If you're interested in doing this, usually in terms of learning, one thing that you look for is things that, like deep learning is a good tool set, right? It doesn't really matter if it's things that you look down further down the line. But one thing that you look for is like really strong signals that is actually much harder. Usually there are things that stronger signals and just images if there was such thing as but there's actually research around this area using signals of motion. So there's actually data
Awesome. Awesome. Yeah, that would be great. Thank you.
I think the role lab at Stanford has video data sets.
Yeah, definitely. I'll take a look at those.
Yeah.
Sorry. Yep.
Thank you so much
Thank you.
for sharing your work. Cool. Next up, we have Sahil. Are you ready?
Hello, hi everyone. Yes, I'm ready with my talk.
Did I unmute?
No, you haven't unmuted.
We can't hear you.
Yeah, hi.
Cool.
So I'm Sahil. So,
Go.
Savya, I think you'll have to switch off your microphone.
Oh, yes.
Hi, I'm Sahil. I'm currently working as a data scientist at a social sector startup, FarmGuide. The problem that currently we are working on is that in India, every year, around 5,000 farmers commit suicide. And the reason for that is that the interest rates on the loans are very, very, very high. Like the interest rates in rural India are something of the order of like 60–70%. And that's because the farmers are not able to get loans from the formal channels like banks and other formal NBFCs don't give them loans. So they have to rely on money lenders for loans. And as a result of that, like because of the huge and also the lack of infrastructure, like in India, in many places, there are no irrigation canals and all. And like also it can happen that like if rainfall doesn't happen, then the crops fail and many farmers end up committing suicide. So this is the problem that we at FarmGuide are working on solving. So so now there are two aspects to it. So one of the aspects is that like most of the authentic data to if a bank or so how we are planning to solve this problem is that we want to enable the insurance companies to to sell their insurance policies at a to a larger number of farmers. So what happens is that most farmers don't even know that uh, most farmers don't know that, like so most farmers uh, are not able to give a proper authentic proof of how much land they own and what crop they grow on the land, because that record uh, because there was a lot of corruption and everything related to that record. So we digitized this whole thing. So that whole record that was kept with the government of what land a farmer owns and what crop he's growing on that farm, we worked with the Rajasthan government and we digitized that process. So as a result, what's happening now is that from the thing that we have built, insurance companies are selling insurance policies to farmers, and they are able to, from their website itself, they are able to access the record of every farmer. So if a farmer comes, he has to give his unique identity. It's called Aadhaar in India, and from that, an insurance company can see what he's uh, so what is the land area of that farmer and where that land is located and what crop he's growing, and from that he can issue insurance policies. And from our portal, as of now, insurance policies of the order of $25 million have been issued. And apart from it, so the problem with crop insurance is that it depends on a lot of factors. It's a massively loss-making business. So whatever companies earn money, it is mostly through the government subsidies that they make money, and not only in India and everywhere. It is just too bad. And the reason for that, whenever we talk to people, like, they would say the same thing, that crop insurance is one of the most tricky things. It depends on a lot of factors. It depends on whether the irrigation canals are present in an area, what is the land area on which the farmer owns grows a crop, what is the crop he's growing, what is the soil fertility level of that crop. It depends on how the weather is going to be like in that area, etc., etc., etc. So what we want to do is that we want to decrease the we want the farmers to be able to get a good enough price back in case their crop fails. So the only way we believe this can happen is using satellite imagery. So, and the reason for that is that, like, the so many cases that I talked about, that, like, whether the irrigation canal is present, not present, how the weather pattern is evolving, etc., etc., etc. Such kind of a data at scale can only be obtained using satellite imagery. So what we have done as of now is that, so we have been able to we have written a code for doing segmentation of satellite imagery, dividing that whole area into different farms, and like, so for a couple of crops, identifying which all farms are of that particular crop, and then just observing how those, like, which all of those crops are failing, and the ones that are failing, from that gain data for that crop failing and all. And once that is created, we'll sell that model to the companies.
Okay. Sahil, you'll have to wrap up in another 30 seconds.
Yeah, sure. So I'm done.
Cool.
So questions?
So, any questions? Yeah. Are there any problems in getting the satellite imagery?
So what we have done is that, so we have done a very hacky thing right now. So we just so we ran Google Earth on AWS, and we scraped the whole of India using Google Earth. So it's so otherwise the satellite imagery data is very, very expensive. So the cheapest way to get that data was just to run Google Earth on AWS and then just scrape the data at scale. We ran like 1,000 instances on AWS and just scrape the data from there.
Wow, cool. Yeah. Just curious, what is the resolution Google Earth provides?
So the maximum resolution was like 1 kilometer, and that's decent
Wow.
enough.
Okay. Cool. Thanks so much, Sahil.
Sure.
So now we have Lubomir. Thank you so much.
So, my name is Lubomir. I'm a consultant in the Bay Area, and we're talking about breast cancer detection. Is there a page down? I've never used the Mac for the record. Okay, so the problem is kind of obvious. We like to detect breast mammograms, which are routinely taken.
Sorry, it looks like. Sorry for the interruption. I think this is not being shown on the handout. So, save to desktop? Oh, I see. Yeah. That's it.
Oh, reset my clock if you don't mind. Okay, so goal is kind of obvious. As you know, millions of women take breast mammograms every year, and the goal is to detect whether it's cancerous or normal, so we can treat it early. Currently, it's done by a radiologist who manually review the image and make recommendations for follow-up, but that has a lot of false positives and also lots of false negatives. But it turns out that from public health perspective, it's real problem, the false positives. So maybe deep learning can do better. This is a classic mammogram. It's a high resolution image. It's distributed in a DICOM format. And when you shrink it to size which is amenable to current deep learning networks, you can see nothing. I cannot see anything. You can see it now because it's high resolution, but when you're shrinking, it's almost unreadable, just so that you know. Anyway, we used two data sets. One is called DDSM from USF, and the other one is called DREAM Challenge. The DDSM is 10,000 mammograms, half of them cancer, which is very unusual. The population percentage is much lower. The DREAM Challenge, that's something like the Kaggle for medical problems. And of course, Kaggle also has medical problems, but this is exclusively medical. And they released a challenge for breast mammography, which has 640,000 mammograms. Some of this arithmetic is not quite right, but bottom line is it's about 300,000 for training and the rest for validation. So we tried this approach, which is kind of self-explanatory for people who took these courses, converting DICOM to PMG, rescaling, coloring, and then fine-tuning in existing ImageNet models, these three listed here. And this is the results that we obtained. Very similar, this is on DDSM data, and I'll comment on the other data shortly. This is using either GoogleNet and Caffe. We did this in a BJ era before Jeremy. And then after that, we learned about Keras and all that stuff, and we used VGG16. The results are very consistent, which is good. This DREAM challenges, then we applied this knowledge to the DREAM challenge for mammography. It's very peculiar challenge, unlike anything else. The trick is that you don't get the data to download, which is normal. but they keep the data. You have to send them your code as a Docker container. Then they run it, and they tell you what's the result. So one cycle of doing this is about a day. If you have somewhere missing comma or +2, as I mentioned, while the mic was off, there are 1,300 registered participants, and only 30 teams produced any kind of result. And most of these results are random, about half of them. So here are the summary of our observations. The teams are ranked by AUROC and area under curve, which I showed you moments ago, and also secondarily by partial AUROC. Partial AUROC is the AUROC above certain level of sensitivity. So we achieved 0.83 AUROC on the DDSM data. On the DREAM data, it's dramatic drop-off, 0.62. I think state of the art is between 0.85 and 0.90. This is based on the papers we read on this topic. So here is a list of things that were working or not working. The fine-tuning made a lot of improvement, even though we used ImageNet tuned a network, it still worked pretty well. The ResNet was totally unsuccessful. I just couldn't get it to work. One feature that had a lot of impact in our hands, when I say our, I do this with a friend, was that the coloring had significant impact on Google Net performance. I'll show you in a moment. And ensemble learning made a difference up to 5 models. Then the performance converged after about 200 to 300,000 images cycled through. We couldn't make any difference with learning rate adjustment or dropout, which is maybe strange, maybe because lack of time, probably the latter. The results are hugely different between DDSM and DREAM images. It could be because these are older. The DDSM is almost 20 years old. I think DREAM is much more recent. I don't know for sure, but. And finally, the probabilities which are produced by these deep learning algorithms are unusable because they're all either 0 or 1 almost. In clinical use, you need something more informative. So that's a problem. This is a colored mammogram. We did this pretty much by guessing until get something that looks more appealing to us. And these colored images look much more clear, at least as far as I can tell. But and the network also performed better. But it's really heuristic at this point. So next step would be to figure out a way to train the network using AUROC, not the accuracy, which is the current metric. Introduce the tumor localizations, which would be idea which Jeremy talked about. Yeah, just to go through this and I'm done. On Monday, in the lung context, tune the parameters more systematically. We were mostly guessing or not even tuning so far. Increase the image resolution. That's the answer to your question. We couldn't get to it yet. This optimized coloring, I don't know what that was about. There's various ways to do resizing. Maybe there is a better way, again, from the recent lecture. Try to get ResNet to work. It's got to work. We just couldn't do it so far. Deal with the output probabilities. That has to improve if this is become useful. And maybe apply the GAN models, adversarial networks. Any questions or ideas? Please come forward. Thank you.
Performance radiologist?
It's roughly as best as I can tell, about 0.9 AUROC. Maybe between 0.8 and 0.9.
And the human performance, radiologist performance, is not nearly good enough. There's been a lot of problems with these breast cancer scans. Yeah, that far too many people end up getting follow-up unnecessary biopsies. Reducing the number of scans.
So for this to get into clinical use, it has to be noticeably better than that. It's not quite there yet, but it's promising. I mean, given what these images look like when you look at them at 224 resolution, so it's a blob. So the fact that it can discern something out of it is good. Yes.
So one thing that I guess in terms of the actual changing of Google architecture, I would definitely think about like in some way, even if you stick with the current size, if you actually, but for the past like 2 months, I've been helping project about contact MRI data set, and we sort of facing the same trouble. But I think one thing that can get out of it is that amount of training data, that you can pick up like your initial layers can actually learn. That's one thing. And in terms of the actual heuristic approach, that's pretty cool. One thing I would do with that is there are actually other networks, there are other like connects that help you to look on that in terms of the actual segment. That's another thing that.
Yeah, we thought about how to improve coloring more intelligently, but again, there was not time because of these crazy rules. So we spent most of the effort on the leaderboard at all. Yes.
I'm curious, what is the general, feeling in the radiologist community? Are they supportive of this research completely, or are they like, okay, this is going to replace our jobs, kind of a?
It's relatively new, and maybe Jeremy can comment because his company is.
By far, the vast majority of radiologists. I suspect that increasing the resolution is going to be 10 times better than everything else.
That's a useful
using some
hint.
kind of attentional model, perhaps.
Yeah, but why attentional model?
Because
it's already in high resolution, so you just need to reduce shrinking.
But you're doing 224 by 224.
No, but that's after shrinking. The original image is 3,000 by 4,000.
It's just, I mean, not shrinking it so much is what I mean. Increase the
Yes.
resolution of what you're looking at.
Yes, but that, I mean, the only thing that has to happen, I think, is to get the network to work with that higher.
There's going to be some limit to the maximum memory you can use. Whereas if you use more of an attentional type model, then you can have a dynamically zoom into the part that's most likely to be useful.
Oh, you mean the localize the tumor?
Yeah.
And then show that tumor in a higher resolution.
Yeah, although with an attentional model, that's done more. That's done as a layer. You know. The Google Street View house numbers paper was one of the first to do that.
What do you think about the approach which you suggested in the last lecture, which was take the set which is already has a tumor localized, and train a network to find the tumor?
Yeah, that would be the easiest way to do it. So two stages, one to find a few potential areas.
Thank you
so much.
You're welcome.
So I'm super excited to talk to everyone today because it's kind of a privilege having so many amazing kind of deep learning enthusiasts in the same room. And it's great because normally when I do this presentation, we're not talking to a group of specific deep learning experts, but it's more to the data science community in general. So I added way too many slides for my presentation. I didn't get the memo about 5 minutes, so I'm kind of going to cherry pick ideas. But I will talk a little bit about the nonprofit that I started 3 years ago, which is called Delta Analytics, and offers free data services to nonprofits both in the US and globally outside, as well as I'll talk about one specific project that I'm co-leading right now, scientist, and we're using neural networks to prevent illegal deforestation from happening. And I think this project is actually like exciting to talk about because it has such interesting problems that kind of if you probably see in a lot of your work, and so I'll spend a little more time there. But I'll first talk a little bit about Delta. And so Delta was started really because when I first started my career, I just was very disconcerted by how technically rich my environment was, and how different it was from the environments that I grew up in South Africa, Mozambique, and now Kenya. And I wanted to do something about it. And what we did, and actually the community is pretty large now. We have 88 data scientists, and we do cohorts every year. And oh, sure. And what we do is like we try and fill the skill gap by offering free data services. And we're very specific in the type of nonprofits that we work with, but really what we're trying to do is for nonprofits that do have data, that have already invested in collecting data, but are not empowered to use it, we pair them with a group of data scientists, engineers, and economists for a period of 6 months. And this has been super fun because it's a combination of technically bridging that gap, but also creating this community of people who are professionals but are volunteering in their spare time. So who do we serve? We have done 27 projects so far, broad spectrum, but I'm going to jump ahead and I really want to talk about like the Rainforest Connection Project. So this is our team, and what are our goals? So Rainforest Connection, their goal is to stop illegal deforestation, and they have currently 3 sites: Peru, Brazil, Ecuador. Our goal is to help them get closer to that, and our 3 goals for this 6-month project is to firstly detect chainsaw noises from audio stream from these rainforests. Our second goal is actually this is pretty important for Rainforest Alert, is that we don't want to just tell them when it's happening. We have to kind of tell them directionality because it's very difficult to get through the foliage. And then the third one is that we're really contributing to their production code and helping them deploy their alerts. And so it's, since there's limited time, I will go through our experiment setup that we're doing next week in Berkeley to try and get at directionality, because it's a very fascinating problem. But I'll spend most of my time talking about just the detection itself, and then I'll share the slides afterwards. So the detection problem, let me first talk about the data input. So we're leveraging these recycled cell phones, and they're placed in these 3 sites, and they're powered by solar panels. So we're streaming data throughout the day from these sites, and we also have metadata, so things like the time of day, anything that your cell phone would send if it was powered, we have that data. So we actually have a very rich data set. And the goal is to send these alerts in a timely fashion. So not only is the goal to detect, but so that our conservation partners can immediately go out and prevent illegal deforestation. And so the initial approach is to turn the audio detection problem into an image classification problem. So we're converting wave files into spectrograms, and then we're applying a classic architecture, CNNs, to classify these chainsaw events. This is where it gets interesting. So just to kind of lead you through the whole flow, we then output a probability, and based on this probability, which we set the threshold very high because, again, very similar to your case, a false positive is very detrimental because we're sending these poor conservationists into the field thinking that they're going to find illegal deforestation. So we set the threshold high. This is where I think it really gets interesting, and as a data enthusiast, this is fascinating to me. So the first is like our lack of any ground truth. So really, we started out with a painfully small labeled data set, and now like our training data set is really just hovering below 2,000. So we're still very small, and then we're doing a lot of augmentation, and we're doing pseudo labeling, which we are familiar with from part 1. But the other interesting kind of element to this is that the way we built our data set is really by kind of grabbing what labeled examples we have from each test site. But remember, all these test sites are in fact very different. So we have Peru, we have Brazil, and like we have most of our labeled data from one site. And actually, like I guess there's 2 issues here, like where one can be addressed by like the structure of our data set, and we're using a balanced data set, which is part of our limitation on size. But more interesting is that there's fundamental differences in the data distribution at each of these sites. So the way that we deploy has to account for this. And like other interesting factors is that when we train, it might be very different from the test time. An example of this is that we didn't anticipate mosquito season, and they're actually at very similar frequency to chainsaws, unfortunately. And so elements like that, as well as weather, so the presence of rain. And this is where like some of the things that we're excited about experimenting with is that AudioSet was just released by the Google team. And so actually AudioSet, most important is probably like the like environmental sounds that they have, as well as they do have power tools, but like really becoming more nuanced with the not chainsaw, so so that our algorithm can really tell what is not. The other thing is that we're not really using the metadata right now, which is pretty powerful because not much illegal deforestation happens in the dead of the night. Most deforesters want to get home. So like that's like an easy thing that we can do next. And so like some interesting architecture models that I've been looking at are kind of like this wide and deep that also Google is now part of TensorFlow, where you complement like your deep learning architecture with a very simple like linear model that kind of imposes some rules. So
we did that in lesson 7 as well.
Pardon?
We did that in lesson 7 as well.
Oh, excellent.
Image dimensions going in as well.
Oh, I think,
Yeah, that code.
yeah, that's excellent. The other related kind of thought of research is that there's actually a lot of data besides the metadata that we could supplement with this, because really, like, if you think about it, it's a physical occurrence and it's in a particular area. So like the probability that the next deforestation will happen in a kind of surrounding area is higher than it will happen like from that area. Like once you start an illegal site, you're probably going to move incrementally. So right now we have no relationship between sites that have previously experienced deforestation and new sites. So there's a lot that we're not leveraging right now that will make this model, which ultimately is like a probability risk model, a lot stronger. So just to kind of, oh, thank you. I'll stop there. I think I will share these because this is also like a fascinating research question, which is really like, how do we make this useful? Because directionality of sound is very hard to kind of pinpoint. And with right now, like our guardians capture a really large area. So I would appreciate any thoughts on that particular piece. The way that we're going about it now is a fairly exciting but probably costly experiment of actually setting up guardians in a different, in a particular structure. But maybe there's ways that we can do this without a physical setup. So I'd be curious to hear.
Thank you.
So actually adding on to Jeremy's point, like, can we embed bounding boxes in a set of areas where the deforestation is?
Absolutely. I mean, I think that, do you mean like on satellite imagery, or do you mean, oh yeah. I actually, I think there's another student in this class who does satellite imagery for this specific use case. I don't even think it has to start with bounded boxes, but we should just be using that type of data. Essentially, I don't think it would be, since our sites are so specific and we know what our sites are and what our areas are, I think we could just start by supplementing with satellite data and having a combination. I don't know, Jeremy, what do you think?
Yeah.
Yeah.
Yeah, I mean, I think this thing of including other types of metadata doesn't require, that's what I tried to show in lesson 7. It doesn't really require any special anything. It's just another bunch of inputs to your Keras model.
Yeah.
And you just jump into it.
Yeah, and it's easy pickings that we're not doing anything with right now. So I sense that we're going to see a big improvement just from doing that.
That's a really dumb question. Why do you have to have a high threshold and then send them into the field? Why can't you have a human listen to the recording and check that way?
That's actually a production issue. So right now we're just using AWS to kind of save our model, score, and send an alert. But we haven't set up the infrastructure for that to be a possibility. Yeah, the same way, what would be powerful is if our conservationists could label data for us when it's not correct, but that doesn't happen right now.
This is our own project. 2 questions. One, is there anywhere, if you're interested in ideas, is there anywhere that data?
Oh, yeah. So our conservation, so Rainforest Connection has given access to the data. From the metadata, there's a lot. They haven't given us access to that whole database. They've given us access to the ones that we specifically requested. But I'm sure the list goes on. Right now, what we're starting out with using is very simple, site location, so we can start to capture the site, and then time of day, and then I believe the other one is the gradient itself, which is actually pretty interesting because some of our gradients are faulty, they're not consistently maintained. They're all powered by solar power, so that's also another one. Yeah. Go ahead. No, please. Yeah.
This was the thing way back. I'm not sure what the end of it is. There was a company that went into the very, very cheap drone that cost somewhere around $5. That actually does checkup like that.
Oh, interesting.
5 years behind now, 5 years ahead, cheaper.
That's interesting.
And that actually keep going if you use that. It wouldn't be much hard for something to fly and check something moving and go back.
Yeah, I love that. I think that's great. Yeah, I mean, please send me the name. That's really cool. Thanks, everyone. Please.
So I'll be talking about role of AI in disaster response and resilience. I would like to start with a story. 8 magnitude earthquake hit Nepal in 2015, and some rough stats on to understand the intensity of it. So thousands of people were killed, millions were displaced, and hundreds of thousands of houses were destroyed. And $432 million was requested for the fund, the emergency fund, and 82 million were delivered in the first month. So as you can see, the impact is big, and there's definitely I'll show you some ways where we can make things more efficient to cover up for the funding gap. So I got really, as I was frantically browsing through the web on researching about charities whom I can coordinate with and help out, it was not very clear to me. I came across something called Digital Volunteers, Digital Humanitarian Network. And this is what they were doing. So that they, thousands of volunteers spread across the world, they were manually actually tagging the social media content. Is it referring to a need, an urgent need, or and is it actionable? Things like that. And this is the output of that whole exercise. So they were able to actually map various needs and offers to help on a map so that the humanitarian workers on the field can easily filter the content and actually target their aid. And the second one is really exciting. So most of the Kathmandu area didn't have detailed maps before this earthquake. So, and those were the worst hit areas. So how would any aid worker supply aid if he doesn't know how to get there? And luckily, there was a student who started building this maps a few years ahead, and he was able to launch this detailed map within 24 hours by crowdsourcing the road. So people were actually looking at satellite imagery and marking the roads and buildings and so on. I thought it was pretty amazing. So some challenges, right? Disaster assessment is long and inefficient. There are usually 3 phases of assessment: rapid, detailed, and continual. The rapid assessment usually takes a week. So, and there's a huge gap. The gray part is the unmet needs. It's just increasing. So clearly, all this is what has been done is great, but clearly we can do better. So some proposed ideas. Can we build an intent classifier for all of social media? So can we say, okay, these people really need help immediately, and is this actionable? Does the social media tweet or Instagram picture have a geotag, which makes it more actionable? Can we easily verify this content? Looks like there's a lot of leverage if we can do this. Another angle here is using satellite imagery. Can we detect infrastructure damage? Can we look at the buildings and see which ones have been destroyed and how much? Can we identify blocked roads? I've personally seen lots of aid organizations really struggled navigating this logistic challenge, especially because the roads were blocked. And many people were actually causing more trouble than helping because it was causing congestion and so on. And can we also detect number of people displaced? Another angle to this is, can we leverage phone signals to detect the displacement? How are people moving after disaster has occurred? Apparently, this displacement also shows how the diseases were going to be how the diseases outbreak. So it's really important for aid organizations to know where people are moving. So some more thoughts for future. So can we leverage sharing economy? So ultimately, if we can enable the community to help each other quickly, that will be the big win. So can we leverage sharing economy? For example, Airbnb has helped its users to offer their homes for free for refugees. So we already have this infrastructure. Can we enable those infrastructures better in the case of disasters? And some more. I'm going to put this on the forum. I would like to acknowledge this book, most of the ideas and the domain knowledge I gathered from this book. And there are also some market incentives. So most of this technology can be used for business purposes. Looking for, we really need to be data-driven. We need to treat this as a software project where we get the requirements from the users. In this case, the users would be the aid workers or aid organizations. So if you have any contacts or pointers, I would like to talk to them. On the technology side, also on the domain side, I think it's important to understand what are the metrics. Based on statistics, 50% of the nonprofits have zero or negative effect. So it's important to know what we're solving and measure to make sure we're actually solving it. On the tech side, yeah, if you're motivated to solve the problem, please reach out. And we need various expertise, satellite imagery, social media, and so on. Thank you. And especially, I would like to hear feedback if you think this is not going to work. Yeah.
I guess one thing that you can, if you're actually like going about it to solve it in some way, I would go about like trying to solve one of the problem. Because in that way you're going to get more resources from within entities.
Yeah.
And from what you mentioned, it looks like the satellite imagery, the actual text and stuff around, something interesting. It's kind of like with the social media, not to name names, but they're looking into things like, like early suicide detection, things like that. That's one way you can segue.
Right. Yeah, that's helpful. Yeah, thank you. So you think social media would be the low-hanging fruit among all these? Yeah, that's a good point. Thank you. Cool. Initially, I started off with satellite imagery, but then I started, I wanted to make sure we're solving the right problem. Do organizations have less data, or would this be just even more burden on them, right? So after some of my research, even I feel like social media might be the low-hanging fruit. One, like they're already trying to, deal with this huge amounts of data. So any help we can give them would be likely positive. So impact-wise, I think social media would be the best option. So I'm interested in that, but also keep eyes open for other opportunities.
The things with the social media is like when there is a disaster, so there might be a lot of false positives as well. So some kind of like a sentiment analysis might go wrong in a disaster recovery place. So you need to think about that perspective as well.
Exactly. Yeah, so that book also mentions that apparently during disasters, the noise is too much, like 20% of the tweets are fake. So we need to really be, especially if the disaster is human caused, like wars, there will be people who will try to sabotage. So it's even more important to be cautious. Yeah.
We can go after like visual impression. I'm not sure if the course will get into it or not, but there's like a whole area of reasoning. It's like something that if you have a threshold of reasoning to do something, reasoning and event. So like if you have that target goal, then you can go about it. That's whatever you can help it. So those are like sort of things.
Right, yeah. So, yeah, cool. And yeah, so another thing they've talked about a lot is, there are volunteers usually when these things happen. So people are willing to help. So we should try to leverage that for gathering the training data as soon as possible, maybe through read captchas or, so that we can quickly train and deploy. Yeah. Cool. Thank you.
Good.
Thank you. Thank you, everyone. Thanks to all the speakers for giving us your Friday evening and all the participants on the, yeah. Thanks so much.
Thank you.
Thank you.
Thank you.
Thanks, Janardhan.
Yeah, thanks. See you guys.